All right, so I hope everybody enjoyed their lunch and is feeling full, but not so full that you take a nap during this session. I think they fed us a little bit too much. That giant cookie at the end was not needed. But in any case, my name's Jerry Miller. I'm a professor at the University of Oklahoma, and I'll be moderating this session. We have 4 speakers this afternoon. Each will have about 20 minutes, hopefully closer to 19, so we can transition. And we're going to hold questions until the end of the session. We have 10 minutes at the end. If we don't burn that up, we'll have time for questions at the end of this session. So with that, I will go ahead and introduce our first speaker. I'm not going to read the entire bio, but you have it in front of you. So if you want to learn a little more about each of our speakers, please refer to your program. So our first speaker is Dr. Royce Floyd. He is an associate professor in the School of Civil Engineering and Environmental Science at the University of Oklahoma and is a registered structural engineer in Oklahoma. He is also one of the associate directors of the Southern Plains Transportation Center. Of course, we're all happy about the new funding for our center, and Dr. Floyd was a big part of that. So with that, Dr. Floyd.
Thanks, Jerry. Happy to be here with y'all today. Get the coveted after lunch spot and the chance to wake you all up. I'm going to talk today about some work that we've done related to ultra-high performance concrete in the state of Oklahoma and at OU. I'm going to try to keep it on a pretty high level, show some pictures of some implementation projects, talk a little bit about lab work we have done, and hopefully get you all excited about ultra-high performance concrete. I gave a similar presentation to this one to the students last week in my class, and they were telling me about all the TikToks they could make on concrete. So I'm hoping that you'll be excited enough that you'll want to do something similar. Before I start, I always want to acknowledge the students that did a lot of the work on this project. My co-PI, Dr. Jeff Volz, is instrumental in a lot of this research, but also Omar Yadek, who is here today, Dip Bannock, Chandler Funderburg, Raina Coleman, Connor Casey, and a bunch of other students have worked throughout this effort. So ultra-high performance concrete has been mentioned a couple of times already today. It's a relatively new technology when we talk about concrete within the last 30 years. Has a very high compressive strength, typically greater than 18,000 PSI. And what really sets it apart, well, one of the things, I guess, is that it has a post-cracking flexural strength. So we're able to get tension strength after we have initial cracking on the order of 700 PSI or more. It has very low to negligible permeability. It's resistant to freeze-thaw. It creates a great bond to base concrete and also has a very short required embedment length for reinforcement that we've already heard about today to where we can use this as a connection material, repair material, a way to increase the life of our structures. To get ultra-high performance concrete, we have a low water cementitious materials ratio. We optimize the particles within the mix. We don't include coarse aggregate to create a more homogeneous material. And then we typically include 2% by volume of steel fibers, but sometimes it can be more than that or less. Because we don't have that coarse aggregate, it does take more mixing energy. And so this is an illustration of mixing ultra-high performance concrete where you start with a very dry powder material. You add the water, and it still looks relatively dry. You start to get cement balls forming, and by the end of it, you get what I refer to more like pancake batter, Walt referred to as molasses, but it's a very flowable material. So in terms of UHPC research in Oklahoma, we've been involved in around 8 projects over the last 6 years that have been sponsored either by ODOT or the Accelerated Bridge Construction University Transportation Center, which included mixed design development, connections of panels, UHPC link slabs, continuity connections between precast girders, repair and rehabilitation efforts, and then some implementation projects which have moved on to full projects using UHPC. And there are several that are currently underway. Walt mentioned some of them this morning. Today I'm mostly going to talk about precast deck panel connections and girder continuity if we have time. But to kind of start, we looked at, in our first project, developing what you may see as non-proprietary UHPC or open source mixed design, but basically a mixed design using locally available materials. And using materials that are available throughout Oklahoma, type 1 cement, silica fume, slag cement, and a very fine masonry sand, we were able to develop a UHPC mixed design that could obtain a compressive strength in excess of 18,000 psi, a tension strength greater than 1,000 psi, and a cost of around $800 per cubic yard, compared to $3,000 or more for some of the commercially available products. It has excellent bond strength, very low to negligible permeability, and a high freeze-thaw resistance. That I'll show you some of those results in this presentation. So we looked at some different fibers as well. And so this is a plot just kind of giving you an example of direct tension strength. So instead of flexural strength, you often measure direct tension strength with UHPC. But in this case, the black line bars use the typical straight fibers that are included in most UHPC, the dash line bars, or a hooked in fiber. And we can see that typically we get similar performance, but the tension strength is usually a little higher when we use the typical straight fibers for UHPC. If we look at flexural strength, which appears to have disappeared from my presentation, but if we look at the flexural strength and the ductility, we are able to add some ductility to the mix in using those hooked-in fibers. We did extensive durability testing for freeze-thaw, chloride penetration, corrosion, and some other tests using our UHPC as well as some conventional proprietary UHPC products, and we found excellent durability for both materials. So freeze-thaw resistance typically showed no degradation even after 350 cycles. So we always had about 100% relative dynamic modulus, and using rapid chloride ion permeability, we had less than 100 coulombs passed for both materials. So here, my slides got out of order. But if we look at flexural tension strength, we have here a ratio between the hooked-in fibers and the straight fiber specimens, and we see that for the most part, we're going to get a little less tension strength, so a little less flexural strength with a hooked-in fiber, but we are able to absorb more energy if we look at the toughness on the right side there. All right, so to get to kind of the more exciting things, in my opinion, but looking at some of the applications of this material, one of the first ones that we considered was connections of precast deck slabs. The picture on the left may look familiar to some of you all. Those are precast deck panels going into a bridge here in Oklahoma. And if you look on the right side, you can see those non-contact lap splices of epoxy-coated rebars that Dr. Darwin talked about earlier today. So to start with, we cast some specimens in our lab at the University of Oklahoma that were similar to these. These were actually intended for repair and retrofit, so it's not exactly the same application, but we tested both the proprietary and non-proprietary UHPC materials. We used contact lap splices for these specimens. We heat cured our UHPC to increase the speed of curing. And then we tested these in both static and cyclic loading. The videos here didn't want to play. There's not much to see with them, but basically we would load over and over again for about 3 million cycles to look at the long-term behavior or just look at the static load behavior. This is a graph of load versus deflection for a static load test using the proprietary UHPC and the non-proprietary UHPC. You'll see that they have very similar behavior. There's a slightly higher stiffness for the proprietary material that's related to it having a little bit better bond to the base concrete. But in both cases, we ended up with a connection that actually produced a strength higher than the flexural capacity of the slab by itself. If we look at cracking in those slabs, we see that the majority of cracking occurred out in the base concrete, which is what we would want in terms of making a connection with this material. So after completing some of those experimental work projects, I was asked to be a part of one of the first implementation projects in Oklahoma using precast deck panels, which was the bridge over the Lake Eufaula spillway on the dam down there at Lake Eufaula, where they used precast deck panels connected with UHPC. These were full depth deck panels. They were full width, so going all the way across the bridge because of the requirements for the equipment. It was a 2-girder bridge system, so they had to take the panels across the entire width. They had an overhang on each side of the girders, and they had transverse joints and then shear pocket connections to make the connection within the haunch. Here you can see some close-ups of those connections in the mock-up. So they did a mock-up section close to the site so that the contractor could experiment with their methods, so that they could prove that they were able to make these specimens effectively, to place them on the bridge, and to make the connections with UHPC. They tested some different variables in the mock-up, which gave them an opportunity to see what would be the best construction method. Up on the top, left, and middle, they have a couple of different sealants that they used for the bottom of the joint. On the right side, you can see the exposed aggregate surface that was used for all the deck panels. And then these girders were actually pre-stressed concrete girders that had a steel plate embedded in the top to which the shear studs were welded. For the mock-up, they used 2 horizontal axis high shear mixers and a proprietary UHPC material. They placed the UHPC into the joints just using wheelbarrows and some pieces of plywood as a backer to catch the material as it was cast into the joints. You can see on the right side picture, there are some 5-gallon buckets that are being used to provide a head on top of the UHPC as it's curing. Here you can see the bottom of those joints on the bridge mock-up after casting. You'll notice that there is some spray foam insulation along that joint, which is where they had some leaks in the initial casting. UHPC is, again, very flowable. It will find any opening in the formwork that's there, and so the formwork needs to be watertight to keep that material in. Fortunately, those things happened on the mock-up, not in the actual bridge. They were able to correct those issues with some better sealants, and the same sort of problems were not seen in the bridge casting. As part of our work out there, we took some cores from the mock-up to look at how well the material had consolidated, flowed through the joints. So we took a core of the UHPC itself from one of the joints, and then we took some from the interface between the UHPC and the deck panels. And here on the right, you can see the core of the UHPC itself. There are a lot of shiny spots that you can see throughout the depth of that core that are the steel fibers that are distributed well throughout the core. On the right side, you can see the UHPC encapsulating one of the rebars, and you can see that it has very good consolidation all the way around. And some of this material flowed, 20 or 30 feet from the point that it was placed. We also, like I said, took some cores from the interface between the panel and the UHPC joint. We were able to get some that were very close to right in the middle that we could then cut down. So the one on the right, we actually cut down and ran a splitting tensile strength test on that core that had half the UHPC, half conventional concrete to examine the bond between the two. This specimen failed at about 800 PSI. It was hard to tell exactly because in the middle picture, that half UHPC core is still holding the same load as at the point that it cracked. So to put that in context, the expected splitting tensile strength for the concrete in the panels was only 500 or 600 PSI, so that the UHPC provided a bond that was equal to or better than the strength of the concrete itself. So once they got onto the actual bridge itself, they placed these span by span. I think by the end of the project, they were doing 2 spans at a time. But the joints were prepared with these wood strips along the side to cast the joints high so they could come back and grind after the fact. And then on the back of that picture on the left, you can see the shear pockets that are covered up with pieces of plywood. The joints were placed mostly at night because it was very hot when they started in August. So they would cast overnight. On the bridge, they had a gantry crane on tracks running all the way down, so they were able to place the material with a concrete transfer bucket, and they fabricated a chute out of some rubber sheeting on the bottom to assist in placement. Once the joints were completed and allowed to cure, they went back and ground those plane with the surface of the bridge deck. And if you look at that picture on the right, you can barely even tell that there's a joint between those two panels. That bridge also uses expansion joint headers that were cast with UHPC. These were cast after the deck panels were put into place, but before a high-density overlay was placed. And they were at the ends of the bridge as well as the internal expansion joints. One interesting thing that doesn't really have to do with connections, but is pretty exciting about UHPC from this bridge was when they were repairing the approaches, they actually hit some of the structural rebar over the equipment galleries and had to go back with a structural overlay and decided to go with UHPC on this project. So they milled down the concrete surface, did hydrodemolition to create a nice surface preparation, and then cast an ultra-high performance concrete overlay on this project. Here on the left, you can see placement of the overlay. They used a material that was actually mixable in a ready-mix truck, so they were able to do 5 cubic yard batches in a ready-mix truck. They'd bring that out onto the bridge. They would place the low spots first, and then come back with the complete overlay that you see there on the right. This is a picture of the finished overlay immediately after placement. This is actually one of the worst looking sections of the overlay because it was the first they placed, and it still has a very uniform surface and ended up very smooth. They came back in, grooved the surface, and then we came back out and did bond pull-off tests on the overlay, partly for their quality assurance plan, but also to look at bond in different locations of the overlay. So we cored sections through the overlay that we had marked previously so that we would get the thin 1.5 inch thick sections, not the half depth, 6 inch thick sections. We then glued steel pucks onto those cores and used a pull-off tester to measure the bond strength. And there on the right, you can see the end product of one of those tests. And if you look really closely, you can see the interface between the overlay and the base concrete. In terms of the overlay bond strength, we had just 3 specimens that failed at the interface. 12 out of the 18 specimens actually failed the base concrete and not the joint between them. And then we had 3 specimens where we missed the overlay thickness, and we actually cored into one of those deeper sections, and so in those cases we were measuring the tension strength of the concrete. But in the cases where we were actually measuring the bond of the interface, they were between 190 and about 315 PSI. The target was just over 200 PSI, and so they were willing to accept these results as meeting their specification. So, we're getting close to time on this presentation, but I want to talk just a minute about another project that we did in the lab where we looked at using ultra-high performance concrete to create live load continuity between precast girders. This is a picture of an in-service bridge over the South Canadian River where they had used conventional concrete to make that connection. The restraining moments caused by creep and shrinkage and temperature in the girders had cracked that section, and this is a common thing seen throughout the state. So kind of in the first part of our work, we actually looked at building some UHPC connections in the lab, testing them on a 2-span beam system, and looking at the flexural behavior at failure. If we look at cracking in these sections, we see flexural behavior in the girders, we see crushing of the concrete in the girders, and then we saw flexural cracking around the joints, but the strength was controlled primarily by the girders. So kind of to summarize those results, we saw about a 30% increase in load carrying capacity by making those girders continuous.